Okay, let's start. Let me share the screen right now. Okay, yeah, let me also use this annotate and then the spotlight and this one. Hopefully it should work now. Okay, yeah, right. So the last two video, like the first two video lectures were given a continuous time signal, obtaining its discrete time equivalent. That we did it in two steps. In the first step, you would get a sampled version of the continuous time signal, and in the next step, from that sampled version, you get a discrete time signal. So we have seen that to get a sample version, which is still a continuous time signal, you need to multiply it with an impulse train, right? And then only those values are retained. And from that, in order to get a discrete time equivalent, now all you need to do mathematically is, in fact, the x-axis is scaled by a value of t. And of course, this would further involve another detail of integrating it from nt minus epsilon to nt plus epsilon to get its value at n. So these are the two steps. Okay, so then the moment you are multiplying with an impulse train, if you look at in the Fourier domain, this is equivalent to convolving the signal with again an impulse train. So which means you will have now the Fourier spectrum of it placed at omega s, that we have seen it earlier, where omega s is the rate at which the sampling frequency in radians per second, which would be 2 pi by t. So with that, you have all copies placed there. Along with it, the multiplication equivalent to convolution in the frequency domain, and also with a there will be a normalizing factor of it will be also multiplied by a factor of 1 by t. That's what we have seen. And then given this for a CTFT of x s of t moving to x of n, okay, that's in a way mathematically equivalent to changing its x-axis, okay, by a factor of t. So that we have seen that this would further introduce a normalizing factor. The x-axis, the frequencies would be normalized by a factor t, and those two derivations, relationship between the GTFT of x of n, CTFT of xs of t, we have seen. Of course, before that we have seen the CTFT of xs of t relationship with the CTFT of xc of t, we have seen. So with these two relations in place, we have also established the relationship between the GTFT of x of n and the CTFT of xc of t. That's what we have done in the last couple of classes, last couple of the first two video lectures, right? Hope you are fine so far. And now we are going to the other counterpart, where now you are given this x of n. Okay, suppose you want to construct back the continuous time signal, which ideally should be in the current context should be equal to the original continuous time signal xc of t with which you have started. So what is done here? Just like from analog to digital conversion has given you from xs of t to x of n, what we would do now is a digital to analog conversion. We wrote as if this is equivalent to multiplication here with an impulse train again. So that assume that you are getting here with that conversion xs of t. Okay, and then you have a this is what we need to figure out. Okay, you have the impulse response of that system, which we call it as reconstruction filter. Okay, convolving with that would give you xr of t. That's where what we mentioned. Okay, so then xs of t, we know the relation between xs of t and xn. This is again from the last class itself. This is given x of n, how do you get xs of t? Right, all you need to do is you just place them increasing the distance by a factor t. Suppose whichever is there at n equal to 0, you keep it at 0 itself. N equal to 1, in the continuous time domain equivalent, it will be at t. Suppose n equal to 10, it will be at t equal to 10t, 10 times capital T. So that's essentially, this is how you could write it. Xs of t is nothing but summation of x of n into delta of t minus nt. This is what you are doing here. Okay, so this makes sense, right? This is, you are shifting the values by value multiply by integer multiples of t, that magnitude is given by n. Again, this is again you in a way you are scaling the x of n values by putting it appropriate, placing them at appropriate values. So now the next question is, given xs of t, how do you get the xr of t? So this is what we would like to look at. Well, you know that hr of t, what does that mean? If you are giving as in that's being the impulse response of this reconstruction filter, which means that if you were giving delta of t as input, what you would have been getting out of that system reconstruction filter would have been hr of t. Now you see here what you are giving as an input is scaled by a factor x of n, shifted by a value of nt, scaled and shifted versions of the impulse values. Summation is what you are doing. So what you get is again summation, because this is an LTI, linear time invariant system, and in place of, so you, for delta of t you would be getting hr of t. This being delta of t minus nt, you will get hr of t minus nt. So that's the relationship between hr of t and x of n, in fact, because this is convolution and x's we already expressed in terms of x of n. So given x of n, okay, you get the output as hr of n shifted by values of nt, and then you have summation of it. Okay, clear so far? And next step is, see, notice here still for us hr of t is still a black box here for us, right? We have not done anything about hr of t as such. Okay, so that's what we would be doing here. You already know from, yeah, again this doesn't require now much of an explanation, because we have already dealt with it here. The moment you are coming from xc of t to xs of t, what's happening here? You are placing multiple copies. Copy is placed at omega s, getting scaled by a factor of 1 by t, right? So now that was giving, so excess of j omega, if you want to express it, given that original one is from omega n to plus omega n with value maximum magnitude being 1. If that is the case, excess of j omega would look something like this, where you have copies placed at omega s, 2 omega s, and so on, minus omega s, minus 2 omega s, and so on the left hand side, right? What should you get now? Excess of j omega should be, of course, from minus omega into plus omega n, but with a magnitude of 1. And these rest of these patterns should not be there beyond omega into minus omega n. So what can you do? You simply do a low pass filtering here, okay, constant with a constant magnitude of t here, correct? So that will take care of compensating for 1 by t into t would give you 1, and whatever is there would come here. So they are as simple as that. So essentially now what, if you look at here, the first graph is showing you what you have here, excess of t. What is your objective to be achieved is given by this one. So that is telling you what should be the frequency spectrum of this impulse response of this reconstruction filter. So this is your frequency spectrum. We're having from a cutoff frequency of minus omega c to plus omega c, and with a constant magnitude of t throughout this spectrum, correct? So that's your, so this is what you needed, and now you need to figure out what should be the values. Okay, so you already know that this cutoff frequency should be, for example, you know, this is where another copy is starting, so it should be in between. This point will be, anyway, it is placed at omega s, this magnitude is omega n, so this point will be omega s minus omega n. So your cutoff frequency is in between omega n and omega s minus omega n. That's exactly what we have written here, right? And again, if you want to avoid aliasing, omega s should be at least twice, and preferably more than that, the omega n, the maximum frequency, you have it. In other words, so what you do is, well, you take a value in between the 0 and omega s, because see, here anyway this is symmetric and this is symmetric what you have here, so somewhere in between you take it, okay? that typical value that you would be choosing would be omega s by 2 is the typical value that you would choose here. Okay, so if you are choosing that as your value, okay, your cutoff frequency is omega s by 2. You know that omega s is 2 pi by 2 multiplied with 1 by 2. So your cutoff frequency in general that you would consider is equal to pi by t. So now you know what to expect from the frequency spectrum. This is a, what is this function known as? What's the name for this function? Rect function. Good. So you have done the ideal low pass filtering exercise we have done for DTFT, but CTFT I'm sure you have done it earlier. Even if you have not done it, this has been done here. Very simple. 1 by 2 pi into integral over minus infinity to plus infinity. But well, this value is there from minus pi by 2 to plus pi by 2 only that you have taken. And then this HR of j omega is equal to t there. This multiplied with e power j omega t. Well, you need to get here t, so you integrate over all frequencies from minus pi by 2 to plus pi by 2, so you have d omega, and e power j omega t with respect to omega integration will give you jt. You have pi by t minus pi by t, you substitute them, you get e power j pi by t minus e power minus j pi by t. Okay, already there is jt here, that j and this will give you 2j times sine of pi by t, so that gets cancelled. All you would end up here is sine pi by t into t by pi by t into t. This is where you end up. Okay, this is a very nice function. If you write its value at t equal to 0, L'Hopital rule you could apply here to figure out its value, as both numerator and denominator are 0 at that point, and with that you will get its value as 1, and at all other values anyway this denominator is non-zero, and when this will be 0 is this, if you have this t to be any integer multiple of capital T, right, then this would be equal to pi, 2 pi, 3 pi and so on. That is where this value would be 0. So this sinc like function would become 0 at t, 2t, 3t, 4t and so on, and on the negative side minus t, minus 2t, minus 3t and so on. And well, anyway, while you are increasing t, this function denominator would increase, so this value magnitude of it would start coming down, okay, start decaying. So that's HR of t, right? This is the expression we have already obtained. XR of t is nothing but n varying from minus infinity to plus infinity, x of n multiplied with HR of t minus nt, right? So you have HR of t there. So in place of t, you substitute t minus nt. You will end up with the expression that XR of t equal to n equal to minus infinity to plus infinity x of n into sine pi by t into t minus nt by pi by capital T into t minus nt. Okay, so this is the expression for it. So you take a look at here. Your XC of t is like that. You got only these points. These are, for example, your x of n also is this, except that this t will be n and these values will be 0, 1, 2, 3 instead of this capital T. And then the nice thing you could see here is the way it is able to reconstruct at non-integer multiples of capital T. That's the very interesting thing. And also it is also interesting to see how what's happening at integer multiples of T also. Look at here, for example, see, this is you basically have a sinc function here, right? This sinc function is getting scaled by x of n, right? And then this, after scaled, it is shifted to n or nt, n times t, yeah, n times t here, because that is when you get this, okay, and t minus nt. So look at here, whichever value that's contributed by x of n here, for that, for example, at t, the rest of the sinc functions would become 0 at multiples of t, okay. And anyway, at this point, this is x c of t is equal to x of nt equal to x of n. So that x of n value would be retained here, rightly so. And this happens despite shifting. This is not going to interfere with the value at integer multiples of t. And in between, the value is interpolated by the by all the sinc functions coming from each sinc function placed at t equal to n times t. So that's how this reconstruction happens. So the interpolator here is essentially a sinc function. Okay, this is your, in fact, this is how it interpolates. So the sinc function being your nt being very far, of course the value contributed by it would be less. The closest one you could expect would contribute more there to what its value is. Okay, so linear interpolator, linear, if you consider this, is straight line change is there in between to interpolate. But here sinc interpolation will give you perfectly, in theory at least, what would be the original XCFT. And again, for this to give the exact value, you could also see this would happen. Perfect reconstruction is when you are varying n from minus infinity to plus infinity, of course. Okay, yeah. So that was the first lecture. Okay, and then of course something I forgot earlier, and later in the second part B I was mentioning is the expressing the Fourier transform of the reconstructed signal with respect to the DTFT of the discrete time signal. So that HR of G omega multiplied with X of e power j omega t. Okay, so let me give a pause here, and let's see if you have any questions here. Let's address that first. So yeah, any?
Sir, could you reopen the PPT once?
Yeah, sure. Reopen this write-up itself, right? You mean the
Yes,
right?
sir, the document. Yeah.
Sure. Let me do that out. Then let me share again screen. Okay, and a minute. Oh, sorry, not PowerPoint. That's OneNote. Yeah, let me keep my this also. Stop my video. Yeah, tell me.
Yes, sir. Above, could you go a little to the initial page?
Which one?
Scroll up, sir, a little more.
Okay.
Near delta of n, when you wrote that digital to analog, and here. So what this in the first expression, sir, xs of t is equal to summation x of n to the
Right.
delta of t minus nt. Here, what is this delta, sir? Is that discrete impulse or continuous impulse?
Yeah, it's a good question. This is not. It's a good point. Ideally, this should be. Should be actually. Yeah. Even this clarity is missing in Oppenheim and Scheffer textbook also. Like for example, if you recollect, a by d, we were writing it as integral from nt minus epsilon to nt plus epsilon, right? So had it been a discrete time impulse, that integration won't be there. So in the textbook, even for A to D conversion, he is considering as if it is a discrete time impulse. So here you don't worry about it at this point. You consider it as if this is a continuous time impulse itself.
Okay.
I know this would give you, like, for example, then the question would be at except at t equal to nt, the rest is becoming zero, but that will have a finite length, right? That's probably the concern here, is it not?
Yes, sir.
Yeah, that's true. I understand. So you ignore that for the moment. You assume it as if that that is so small, and you treat them both as it is. Probably doing a bit more rigorous math would be, we will be able to resolve even that. But for our purpose, that is fine.
Okay, sir.
That's a good point. Yeah. Any other question? So if there are no questions here, we could move on to. So have you? Yeah, let me see the poll.
Excuse me, sir.
34 of 39 have done it. Okay. Yeah, around 32%.
Hello, sir.
Yeah. Yes. Who is this?
Actually, in getting the in getting the sampling. In starting sampling, we are getting the discrete signal x of n from ss of t by
Right.
integrating nt by integrating over nt minus epsilon to nt plus epsilon, right, sir?
Correct.
Now
Correct.
we are obtaining the ss of t by just multiplying with the uh, impulse train. Will
Right.
this
Right.
ss of t and the initial ss of t will be same or
Yeah.
different?
So yeah, this is again. See, this is probably the not the very rigorous notation as such here. See, again, this boils down to the earlier question posed there. See, this when I am multiplying with an impulse train, okay, which is continuous delta. So perhaps there should be there again something related done in the interval of nt minus epsilon to nt plus epsilon. That has to be done. So see, I would say you look at it this way. You ignore what this box is, okay? What you have is at the end of this black box, you are getting excess of t back, which is same as the 1 minute. Let me go to this and take the spotlight. Okay. Let me also stop this video part. Okay. So you see, you assume that 1 minute. Yeah. Whatever you have here, okay, excess of t is there. You just assume this box is, see here actually inside it there is in fact minus nt minus epsilon to nt plus epsilon we were doing, right? Assume that similar thing we are doing. What exactly needs to be done, let's not worry about this point, but you just simply consider this excess of t is same as this excess of t. With this black box you are getting excess of t back. So that's yeah. So with that, then you will not have any problem with that. This flow would follow then nicely here. No, does that answer the question?
Yes, sir. And also you are actually providing in that digital to analog converter. You are providing that sampling time also, right?
Right, correct. Without that, you don't really know.
Capital
See,
T.
yeah, because that normalizing factor T, this digital to analog converter has no idea about it. So that's important. We give that information there so that it would be placed like this. And again, as the first question is there, this again is debatable whether this has to be this also. I'm not pretty sure how else could we write it more correctly. I do not know the answer at this point, but that's a very correct question. Like this, when I have delta of t minus nt, can I put x of n like this? This is something we need to look at it. But for the since see anyway, all that is whatever there could be slightly varied expression here, but at end of the day what we need to see is this excess of t is same as this excess of t. Okay, that would clarify our things on what spectrum we would be getting at this point. Yeah, good. I'll try to find out if there is a any better way of expressing it, just like we had here for this block integration or NT. Yeah, if you had referred to Oppenheim and Schiffer, that expression would be missing here. You would be directly dealing it as if we are dealing here. I'll try to find out, but anyway, that would be a slightly modified version, but the rest will not have an impact of that because anyway, this excess of t the same as this excess of t. What we do mathematically, just I will try to figure it out if I could find it somewhere where it is done bit more elegantly than this. Yeah, any other question here? Okay, so if there is no other question, just let's quickly go through this part also, the example part. Okay, this again, if you have done it already, it is good. Otherwise also you take this example, please work it out step by step yourself. You also draw it in your notebooks for yourself, starting from the begin part. Yeah, this would come in different forms. You need to do it later also when we do downsampling. See, if you understand these two parts clearly, the rest are a slightly varied versions only. because the downsampling in a way is also equivalent to, given a continuous time signal, you are taking samples of it. Downsampling also, you are, instead of a continuous time signal, now you have a discrete time signal, but you are again taking samples of it, right? You are not taking all. So it will have exactly the similar properties as moving from continuous time to discrete time. Similarly, upsampling has the same feature. See, upsampling is you have some samples, but you are increasing your number of samples. Here you are making it to continuous time. There you will be still in the discrete time, but you will be increasing samples. So once these two parts are clear to you, the rest would flow very smoothly for you. This is where, since you are dealing with it for the first time, initially some effort would be required for getting things right here for the first two parts of it. Okay, after that, even discrete time processing of continuous time signal also flows very nicely once these two are cleared, because all that it does is, see, we are doing a very trivial task here. From xc of t you are getting x of n, and from that you are again trying to get xc of t. Okay, this is not what you want to practically do. You want to do some processing of it. So all you will have there in the next part is this x of n, it will be given to one discrete time system, and you will get output of it. That would come to this digital to analog followed by reconstruction signal, and this will come back, give you the final continuous time signal. So and so all the rest of the parts, so next part will be discrete time processing of a continuous time signal, next upsampling, downsampling, after that upsampling, after that doing upsampling and or downsampling by a non-integer factor, by a rational function. So all these things, whatever the basics required are all will be already covered by the time you are able to establish the relation between xc of t and x of n, followed by x of n and xr of t. That's all. Okay, so spend some time here, and that would help you to sail through very smoothly through the rest of the sampling chapter. Okay, right. So this is a classical example. Again, I took both these examples I have given. Hope you all, yeah, most of you hope have tried working them out. Okay, you please give it a try. If you still get some doubts, those are the worked out examples from Oppenheim and Shepherd textbook. Even the interpretation which I asked for has been clearly given in the textbook. So you put your full effort there, try to solve it, and then cross check your results with the worked out example there. Okay, so let's come back here. Cos of omega naught t is there. Okay, we want to go through this whole process now. So first, you xc of t, the moment you see cosine and sine, the way you do it is you write it in terms of complex exponentials, right? And then you solve it out, because you know for the complex exponentials being eigenvectors how to solve it. So this is 1 by 2 into e power j omega naught t plus e power minus j omega naught t. E power j omega naught t is 2 pi into delta of omega minus omega naught. There is anyway 1 by 2 factor is there. So for cos omega naught t, you are getting pi into delta of omega minus omega naught plus delta of omega plus omega naught. Right? So you come here now. So at omega equal to omega naught, there is a continuous time impulse, right? And its magnitude getting multiplied by pi. Similarly, this would give you another continuous time impulse at omega equal to minus omega naught, again multiplied by pi. So that is your xc of j omega. Okay, and then yeah, I could simply write here xc of j omega, even dropping this, because this anyway is because those values are being real, I think, right? Okay, next. So now you are doing you are multiplying with an impulse train, so the copies are kept at omega s. So assume that initially there is no aliasing. So what would that ensure? There is no overlap. So that's greater, omega s is greater than twice the omega naught value. So this being omega naught, this being omega naught, 2 omega naught, this gap being more than 2 omega naught, you will have omega s by 2 somewhere in between here, correct? So that you multiply with t. So of course, in that case, will get back your signal x in xr of j omega here, right? That's the case here. Yeah, I was drawing with red. I should have drawn this also with red, but anyway, that's just not a problem. Okay. Now, suppose the tricky part would be when your omega s is less than 2 omega naught. So assume that your omega s is less than 2 omega naught. So this is where you need to keep the first copy after 0, right? So this this width would be omega naught, but your this omega s distance is less than omega naught distance. So this copy, left hand side of that copy, which I'm left side is indicated by red and right side copy is indicated by blue, would come here. Okay, and then where will that come? This width is omega naught, correct? And this is anyway omega s. So this distance would be omega s minus omega naught. Similarly, one copy on the left hand side, again at minus omega s. By the same logic, this would now instead of the left copy coming there, okay, now the right side copy of the c, this whole thing is, wait, this pi by t, yeah, this whole thing we are placing it. So the right side the left side copy would come here, which is there at minus of omega s minus omega naught. Now where is the cutoff frequency? It is pi by t, or in other words omega s by 2. What we know now is omega s is less than 2 omega naught. So omega s by 2 will be less than omega naught. So this won't be there, somewhere here it would be there. But again, you could also see here from the same expression, this omega cutoff will be greater than omega s minus omega naught. From there itself you could figure it out. So this multiplied with t, okay, that would give you the reconstructed signal. Now having copies at omega s minus omega naught minus of omega s minus omega naught. Now you take the inverse CTFT of it to have cos of omega s minus omega naught into t. So with aliasing, it looks like as if this is what you would be getting. I think Akansh was sometimes sending me one demo given by Openham's thing. So this was exactly the very example, very similar to this. If you understand this, that part you will understand very clearly why what's the role of sampling here. Okay, yeah, 2 examples were given here. So hope I leave that examples to you to work out and then come back and check with worked out examples in the textbook as well. Okay, so any questions here so far?
Sir, in the without aliasing part, in the previous example which you have shown, so did you take omega naught as pi by t because you have written omega s minus pi by t?
No, it is not omega naught I have taken as pi by t. It is omega c I have taken as pi by t. See the cutoff frequency. Let me write something here. See, there is one thing is cutoff frequency is there, right?
Yes.
So this cutoff frequency, if you recollect what we did, should be equal to omega s by t, right?
Yes.
So because if it is there from 0 to omega s, this side anyway, it will be there for till omega n. This side also, when you are keeping copy, it could come to omega n, right? So in between we are taking the cutoff frequency here. So this, all we are taking here is, this is 2 pi by t anyway, if I know t value, correct? So omega s by 2 would give me pi by t. That's all I am taking here. Okay.
But the impulse should be at a distance of omega naught from omega s, right, sir?
Correct, correct. You are right. So look at here. So first copy is anyway at omega naught and minus omega naught. Okay. So the second copy is starting, you need to place it at the same thing, you need to place at omega s, correct?
Yes.
So this distance would be equal to omega n now. Is it not? That distance
Yes.
is omega n.
Yes.
This distance is omega s. If I take this distance, it is omega s, correct?
Yes, sir.
So then I get your question. So what should be there is, yeah, I should have written, sorry, this should have come here actually. Cutoff frequency is here.
Yes, sir.
Okay, you are right. So I wrongly marked it at pi by t here, right? Is that your question?
Yes, sir.
Yeah, good observation. That's correct. In fact, that was a mistake. So this cutoff frequency would be here. So that 1 minute. So omega, what did I write here? So the cutoff frequency should be at pi by t. 1 minute. Let me work it out. So yeah. Yeah, just let me see that out. So omega naught minus omega naught is there. Okay, the next copy is kept at omega s. So this would be equivalent to omega n. So this, if I have to write this, all I could write here is omega s minus omega n. That's all I could say here. That value is equal to omega s minus omega n. Okay, but the cutoff frequency would be equal to, what would be the cutoff frequency? Will be equal to pi by t.
Pi by t.
I should have written it as omega s by 2. That's equal to pi by t here. Am I clear now?
Yes, sir.
Okay, good. So the whole thing is pi by 2t, and this is omega 2 pi. Whole thing is 2 pi by t, and the cutoff frequency is at pi by t. This, if I have to write, this is equal to 2 pi by t. Okay. Is that clear, or is there any still some confusion is there here?
No, sir, it's clear.
Okay, good. That's a good point. That was, yeah. Any other question? Yeah. Is there any other questions here? Then, okay. Good. Today, happy to see 38 students around. Okay. Let's yeah. So I think we could stop here if things are clear to you, and so far if you don't have any questions, we can stop here. Next class would be again on Monday. Let's have it and then decide if it is required. We will have class on Wednesday. Otherwise, we will skip it, depending on how it is going. So mostly probably we could just should be fine. I think now with just one class a week also should be fine. Okay. Yeah, if you guys want it, it's good actually. That's also is not, but let's see. Okay, next week we will see anyway. So if you don't have any other questions, I'll stop here. Okay, let me stop. Yeah, sure.
I have a doubt in lecture 2. Like, can you just open the PPT? I mean, that
okay.
shared document.
Sure. Then I will just stop this recording here anyway.